In my opinion, the key to getting a 5 on the BC Calc test is having mastered Taylor-Maclaurin series. So let's first answer the question. What is the difference between a Taylor and a Maclaurin series? And the simple difference is that a Maclaurin series is centered at 0. So if we take our Maclaurin series, we're going to start with f of 0 plus f prime at 0 times x plus f double prime at 0 times x squared over 2 factorial plus f triple prime at 0 times x cubed all over 3 factorial and on. Or we can, for our Maclaurin series, write the general term, which is going to be the sum of the nth derivative at 0 over n factorial times x to the n. So what's different for a Taylor polynomial? A Taylor polynomial is centered at a. So now our first term is f of a plus f prime at a times x minus a plus f double prime at a times x minus a squared over 2 factorial plus f triple prime at a x minus a cubed over 3 factorial, and we can see the pattern. And now we can write our general term for a Taylor polynomial, which is the nth derivative at a over n factorial times x minus a to the nth. All right, so now that we've got our general form, let's talk about what do we have to have memorized. So these are the ones that you don't want to have to be developing every time you need them. You simply just want to know them. All right, so let's get these down. Before I put them down, you should be maybe even pausing to see if you've got them all. So let's start with e to the x. E to the x, you should, one way to remember is if you think of your function e to the x, it's always increasing and always concave up, and everything is just so positive about it. So we start at 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot 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 plus x to the n over n factorial is our general term. All right, sine x is a rather odd function because recall a function is odd if it has rotational symmetry about the origin. And so since it's odd, it only has the odd powers. So we're going to have x minus x cubed over 3 factorial, and it's going to alternate in sine, x to the 5th over 5 factorial, and this goes on forever, and our general term negative 1 to the n, x to the 2n plus 1 all over 2n plus 1 factorial. By the way, these parentheses around 2n plus 1 are not optional. All right, cosine x is our very even function. Remember, an even function is one that has symmetry about the y-axis. So this is going to take all the even powers. So we're going to have 1. This is an even power because that's x to the 0 minus x squared over 2 factorial plus x to the 4th over 4 factorial plus dot 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 plus negative 1 to the n x to the 2n all over 2n factorial. All right, our last one, 1 over 1 minus x. We should recall that this looks like the sum of an infinite geometric series. There's our first term. There's our ratio. So our first term is 1, and we're multiplying by x every time. So 1 plus x squared plus x cubed plus x to the n. So the quick way to remember these, e to the x is always positive, sine x is odd, cosine x is even, and 1 over 1 minus x reminds us of the geometric series formula. All right, whoops, we want to go here next. All right, so let's talk about finding the interval of convergence for a power series. And in this particular case, I've actually already given you that the radius is 1/2. You guys, I found, are really quite good at finding the radius, but I wanted to practice finding the interval of convergence. So if my radius is 1/2, So r is 1/2. And in this case, where is it centered? Well, we can see that right here it's 2x and it's not x minus something. So it's centered at 0 because nothing's being subtracted from x. So centered at 0. And so the region I'm looking at is from -1/2 to 1/2, and I need to consider what's happening on the endpoints. So first I check to see when x equals -1/2. So I'm going to plug this in the sum formula. So I have -1 to the n. I have 2 times -1/2 to the n all over n minus 1. And let's see what happens here. We've got -1 to the n. Inside here I get -1 to the n all over n minus 1. Now, these are going to be negative at the same time and positive at the same time, which means that top is always going to be 1 over n minus 1. All right, so this reminds me of my harmonic series, and in fact, it's just off by 1. If it was 1 over n, if I plugged in 1, I get 1. Here, 1 over n minus 1, when I plug in 1, well, it's not defined, so I'd start at 2. And when I put in 2, I get 1, and when I put in 3, I get 1/2, and when I put so on. So it is a harmonic series, which means it diverges. So it diverges because it's the harmonic series. And this would be enough answer on a free response about this. So diverges because it's a harmonic series. So I'm going to just put a parenthesis like that. Now I consider the other endpoint. Notice how I'm labeling my work so someone could follow what I'm doing. So when x equals 1/2, I'm going to have the sum -1 to the n, 2 times 1/2 to the n, all over n minus 1. And in this one, I'm going to have -1 to the n times 1 to the n, all over n minus 1. Well, 1 to the n is just 1, so that's really not even there. And oh, look. Well, if this is a harmonic series, this is my alternating harmonic series, and that converges. And a good enough reason on the AP test would to just say it converges because it's the alternating harmonic series. So there's that. And we have that converging there. And we're done with this problem. All right, we're going to go back to Taylor polynomials on this next problem. And let's talk about what I know from seeing a Taylor polynomial. So here's the problem at hand. And I would encourage you to pause the video right now and think about everything that you know about f of x based on this Taylor polynomial. So go ahead and give yourself a moment to see what you come up with before you listen to the rest of this. All right, welcome back. We're going to come up with a lot of the things we could know about this particular function. First off, we would know that f of 1 equals 2. This one is centered at 1, and this first value 2 is the value when we plug in 1. Furthermore, f prime at 1 equals 0. Because there is no x minus 1 to the first power, that means that the coefficient was 0. My first derivative is 0. And as soon as I see that, I know that I have a horizontal tangent. Okay, at 1. Horizontal tangent at 1. All right, let's go with the second derivative at 1. So the second derivative is not 3, it's actually 6. Let's make sure we understand how to get that. The second derivative at 1 over 2 factorial equals that coefficient 3. And that's how we end up getting it being 6. Now that we know that that second derivative is positive, we know it's concave up and has a horizontal tangent. Okay, so now I know that it has a relative minimum. Relative minimum at 1. Okay. Let's see, what else do we know? We can figure out the third derivative. We know that the third derivative at 1 over 3 factorial equals 6. Therefore, the third derivative at 1 equals 36. All right, and I think we've hit on all the main points that we could find just about f, about that Taylor polynomial. Notice that everything we knew exactly about f had to do with what was happening at 1, because as soon as we move away from that value of 1, everything is an estimate. So we can certainly use the Taylor polynomial to estimate the value at 1.1, but we don't know anything exactly about the polynomial except at its center at 1.